So far we've seen essentially the three equations that rule the dynamics of ideal fluids. So continuity equation, which means conservation of mass, Euler equation, so in general conservation of linear momentum, and energy equation, so conservation of energy. In addition to the equation of state, which describes, of course, the kind of gas, and in particular talking about ideal gases, it's the equation that you know very well. So now let's see the physics of sound waves. So what are they? Let's suppose we start with a solution in which the fluid is just in hydrostatic equilibrium, okay? So what it means that if I call P0 and ρ0, respectively, the pressure and the density in this equilibrium cases, so in this hydrostatic equilibrium cases, it means that we consider a small perturbation, which is described by P prime and ρ prime. So in this sense, given that this is a small perturbation, P prime is much smaller than P0, as well as ρ prime is much smaller than ρ0. And given that there is no V0, at the equilibrium, the fluid doesn't move. So the velocity, it's just of V prime. And V prime is small, something small, of course, with respect to what we will see. Given that it is the situation we begin with is a hydrostatic equilibrium, well, you know very well is that if the fluid is subject to the action of some force field F, so F force per unit volume, so this equation has to be satisfied. So, which means essentially that pressure adjusts in such a way to counterbalance the force, okay? Or if you want, minus gradient of pressure is just the force due to surface forces acting per unit volume, so minus P, minus gradient of pressure plus Pf, the total force acting on an element, on a fluid element, has to be zero. Hydrostatic equilibrium. So the situation is this. What about the nature of the gas? Well, we assume, as I said, an ideal gas, and here we make also another assumption on the nature of the perturbation. So the way pressure depends on density. In particular, we can use this this relation here, that if gamma is indeed the adiabatic index, so for example, think of a monatomic gas, in that case gamma is 5/3, but we can assume that gamma can be whatever index, so in particular in two cases. So when gamma is 1, which is not an adiabatic index, you know very well that for any type of ideal gas, the adiabatic index is always greater than 1. But here, we assume the possibility of considering an isothermal perturbation just by allowing gamma to be 1. So if we consider an adiabatic perturbation, gamma is the adiabatic index, so for example 5/3, or we could also consider an isothermal. In the isothermal case, from the equation of state, you immediately see that gamma is indeed 1, because P is inversely proportional as 1 over V, and 1 over V scales proportionally to ρ. So it means that the pressure is proportional to density in the case of an isothermal transformation, okay? So let's apply what? Well, the equation that we've just seen. So for example, the continuity equation in the presence of this perturbation. So the total density now is ρ0 plus ρ prime, as well as the velocity is v prime. Okay, I just did that. As well as the Euler equation. Okay, here I wrote Euler equation, just taking into account the overall density ρ, so ρ0 plus ρ prime, as well as the pressure, which is P0 plus P prime. Mind that P prime, well, P0 is not a constant, it's a function, as well as ρ0 is a function, as well as P prime, as well as ρ prime are all functions, okay? Functions of space and time. With the caveat that all the prime quantities are negligible with respect to the unprimed quantities. So what this means? Well, this means that if you look here, we stop at first order in Taylor expansion. So it means that whenever you have the product of two prime quantities, that's a second order quantity. So we can just neglect it. So let's have a look. You see, here you have, well, first of all, let's consider hydrostatic equilibrium. So it means that the zero quantity, P0 and ρ zero, do not depend on time, because otherwise it wouldn't be a hydrostatic equilibrium case, the initial case. So the time derivative of ρ zero, just zero. And here you see, in the second term of the continuity equation, you have the product of ρ prime times v prime. As I said, this is the product of two prime quantities. So it's a second order quantity. So it can be neglected. So this product can be neglected. Let's have a look at the second equation. You see, let's take this for this term here. Just look at the velocity term. You see, you have the gradient of v prime, scalar v prime. So already this guy is a second order quantity. So everything which multiplies this guy is just second order. So it can be completely neglected. It's a second order quantity because you have v prime times gradient v prime. And here, for the very same reason, you see you have the time derivative of v prime times ρ prime, again, a second order. So away. Just this one, because this one is not a first order quantity. So this guy times this guy cannot be cannot be neglected. That's it. So let's see. Yes, of course, and indeed, minus gradient of P0, just because of the hydrostatic equilibrium, equals plus F is 0. So this is just reminiscent of the initial situation, or initial without perturbation, I mean. So let's have a look what we have now. So here the only surviving term is the time derivative of ρ prime, here it is, times what? Times the divergence of ρ zero times v prime, here it is. And the second one, well, on the left-hand side, the only surviving term is ρ zero time derivative of v prime, here it is, and you have nothing else. The only other term is on the right-hand side, minus gradient of p prime, which, if you bring it to the left-hand side, is plus. Easy, okay? So what we exploited is this perturbation is small, that the initial situation is hydrostatic equilibrium, and we just exploited, in addition to these assumptions, we just exploited conservation of mass and linear momentum. We still haven't used yet the nature of the perturbation, which is described by this relation here. Now, let's see how p prime can be also expressed. Well, p prime is a small quantity, which should be better called as dp, okay? So it's something, again, Taylor expand, is something on, you just express so it's the deviation with respect to the initial pressure to P0, so it's just a Taylor expansion first order. So the derivative of P with respect to ρ when ρ is ρ zero times the shift in density, so ρ prime. So Taylor expansion of this function here. I still have to calculate it, but this is what I'm gonna do. So, okay, let's take the second one, equation of the system here. So the first term is just copied. The second term, here I have gradient of p prime, and I use this. So this is a constant, okay? So gradient of p prime, it means gradient of ρ prime. And here it is. This is a constant, and here it is, because this is This dp over d rho is a function, but it's calculated 1 point. So at one specific value in the Taylor expansion. So the gradient of p prime becomes gradient of rho prime. Okay. Now, if you work out the divergence of all this equation, which is a vector equation, so you can calculate the divergence. The divergence of this guy here, again, is divergence of, you can swap the time derivative and the divergence. So time derivative of divergence of v prime plus what? Well, again, this is constant. So divergence of gradient is nabla square, so the Laplacian. Laplacian of rho prime. But you see here the divergence of v prime, you can also use this equation here. So far we exploited only this. So it's time to use this one. So instead of divergence of v prime, you can write minus 1 over rho d rho prime over dt, which is exactly what I did here. So here I also divided by this coefficient here. So by dividing by dp over d rho at 0, and you replace, as I said, here, you immediately see that you end up with the wave equation. This is indeed the wave equation, which written this way, you immediately see that the sky here and the denominator of this coefficient here is, of course, the velocity squared of the wave, just wave equation, D'Alembert equation. So we call CS, where S stands for sound. This is indeed the speed of sound in the fluid, which is nothing but the square root of dp over d rho, which now we can exploit the equation that the perturbation has to. And you immediately see that the derivative of this guy is you gain an extra factor of gamma, and then if you multiply and divide by rho, again, you get p rho over p0, sorry, over rho 0, which is something that you should already know somehow from your previous studies. CS is usually the notation used for the speed of sound. Why? S stands for sound. But why is the sound? Well, because it's a perturbation within a fluid. You just perturb, you either increase or decrease at one point in space pressure or equivalently density, and then this perturbation propagates, which is exactly what the sound is. So that's why it's the speed of sound. So you immediately see that depending on the nature of the perturbation, and typically, for example, in the air at standard conditions, the perturbation is adiabatic. Then I'll make a comment on that. And there's also an interesting story about this, because Newton, for example, thought at the time that the perturbation was isothermal in the air. This is not the case. So that makes a difference, because of course you see a square root of gamma difference, whether gamma is 1 or greater than 1. So in particular, depending on whether you consider an adiabatic perturbation or an isothermal perturbation. So what is the difference? Well, the difference is, in the adiabatic case, it means that the perturbation, in the perturbation case, the region of volume which is perturbed, so for example, the pressure is increased, it means that the fluid is not very efficient in dissipating energy through heat, for example. So it gets a little bit hotter, but it's not very effective in dissipating this heat through radiation, for example. So if the element of fluid that you're considering is not, you can neglect the heat that can possibly exchange with all the remaining parts of the fluid. Well, it means that it's an adiabatic transformation. So the perturbation in that case is better described by an adiabatic case. While for some reasons that in general you don't know, you have to consider all the aspects, or whether the radiative processes can effectively, on the timescales that are of interest, if indeed radiative processes can play a role, so can indeed contribute to dissipating, to energy dissipation through heat exchange. In that case, of course, the perturbation could be isothermal. It depends. It depends on the conditions of the fluid. So, but you immediately see that there is, in one case, in the case of isothermal distribution, it's just scalar square root of t, which is, again, here the general comment is not by chance the typical velocity that you have for the typical speed for the sound is comparable to the velocity of the individual molecules. Well, that's exactly the same mechanism. The individual velocities of at the microscopic level of the gas, of the fluid, is indeed what makes the sound, what makes the perturbation just propagate through the medium. So it's not by chance that you see that essentially P over rho is indeed kT over the mean molecular weight times m, which is indeed the velocity, the average velocity of a molecule of this gas. But here, what I wanted to point out is the dependence on density. You see, in the case of an adiabatic perturbation, the sound, the velocity of sound, the speed of sound, scales with rho to 1/3. So it means that from a qualitative point of view, in the case in which the fluid, the region of the fluid which is interested by the crossing of this sound wave, in case you have a gradient in density, so in case density, for example, increases along the path of propagation of the wave, it means that the higher the density and the correspondingly higher will be also the sound speed. So it means that in that case, you can end up with the sound moving at different velocities depending on the density. Well, you have no analog in the isothermal perturbation. Okay. Just to give you a feeling of what numbers are we talking about? Well, typically, you might have, in many astrophysical contexts, temperature of the order of 10 to 4 Kelvin. So a few tens, thousands degrees. In that case, I advise you all the time to calculate what the numbers that I show you. In that case, you immediately see the typical velocity, the typical speed of sound is of the order of kilometers per second, okay? And this is very important to remember for the reason that we will see today in the following. And yes, indeed, the fact that the speed of sound can change, in particular can increase, moving to a more dense region, it means that you have at some point, and I'll show you a figure which shows this, you can have the macroscopic thermodynamic variables that you use to describe the state of the fluid, so pressure, density, temperature. At some point, they can be kind of discontinuous. Discontinuous in the sense that they change significantly over a length scale which can be comparable with the mean free path of the particles. In that case, we will see that this is what just preludes to the shock formation. And I'll show you a graph. So this point is very important because that's a natural way to develop shocks within fluids. And shocks we will see that they are described as discontinuities in the macroscopic quantities described. So you have the pressure, and then when you cross the shock, you have a drop or an increase, sudden increase, discontinuous increase or decrease of pressure, as well as density, as well as temperature. We will see that. And indeed, having talked about sound waves, now it's interesting to move to shock waves. So shock waves, indeed, is when some perturbation that happens in a region of the fluid, when the source of perturbation, let me see this way, can move at faster than the sound, in that case, the fluid itself is not capable of readjusting. Because in the end, if you think, the speed of sound is telling you about the capability that one generic fluid has to react, to readjust itself to some perturbation, okay? But if, for some reason, what causes the source of perturbation moves faster than the speed of sound, so then the capability of the fluid itself to react, to readjust, then you have the result is that a shock wave is developed. And as I said, the macroscopic description of a shock, the macroscopic result of a shock, that you have that these variables, macroscopic variables, which describe the state of the fluid, experience discontinuities, which from a classical point of view, if you think, sounds a little bit weird, surprising. So examples in astrophysical context are very abundant. For example, you have the so-called pulsating stars, which are the Cepheids, are Lyrae, that you probably know from the astrophysics course, which are just stars, relatively large stars, which at some point during their lifetime, they make pulsation. This pulsation, they develop shock waves, because the velocity can be larger than the speed of sound within these stars. So shocks develop. As well as I was telling you, supernovae explosions. So that's a beautiful example of how shock waves develop within stars. And this is a dramatic case because the energy involved is of the order of 10 to 51 erg, the energy which is liberated for example, if we think of a core collapse supernova, we have the collapse of the inner core, which then bounces back and develop a very powerful shock waves, which just disrupt the stars, disrupts the entire star. And if you want to study, in my course about multi-messenger astrophysics, we will devote a lot of time just studying the results of the shock propagating through a supernova. That's very, very beautiful physics. You have so many things that concur and play together. And but again, just as I said, so the shock wave in that case is really has an incredible effect. It just disrupts the stars. And also gamma ray burst. Gamma ray burst, which is also a topic which we will study in the course I mentioned. Very important one. Mainly because gamma ray bursts are associated with, for example, with sources of gravitational waves, so something which is attracting most of the interest in now and in the next decades, and because they are so bright that they can be seen at any distance, and they are related to some of the most fundamental questions also, how elements in the universe are created. So for many reasons, gamma ray bursts are interesting, but in this context of shock waves, gamma ray bursts develop shock waves they are the relativistic analog of non-relativistic supernovae. In that case, there's a jet, and the material which is the jet is made of just expand at ultra-relativistic speed. We are talking about Lorentz factor of up to 1,000. So, and you imagine this ultra-relativistic jet expanding through a stellar envelope. So again, the star is disrupted by the presence of this ultra-relativistic jet. So in this case, we are in the presence of relativistic shocks, which have a different physics. You need to use relativity, special relativity to describe. And that's what we are going to do next. So very beautiful examples. As well as H2 regions and regions in general, where you have the formation of stars, in which you have the outflows, the very powerful outflows, which automatically develop shock waves. So this is just a few examples just to prove you the shock waves are, as I wrote here, ubiquitous. And not only in astrophysics, but also in ordinary physics. And I will show you an example, a pretty scary example, because it's about atomic bombs. But we will study the hydrodynamics and thermodynamics of atomic bombs. Very beautiful physics. Well, of course, there's nothing beautiful about that, but the physics is really awesome. Very beautiful. But of course, it's better just to study from a purely theoretical point of view, not experimental. So, and we will see why shock waves. So shock waves are ubiquitous, and why are so important? Well, if I should say in a few words, at least in an astrophysical context, let me put it this way: shock waves are something which they heat matter up. They heat matter up in such a way that then, you know very well, when matter is hot, can emit radiation. So in some case, we just detect matter because of the result of the heating by a shock wave. Shouldn't there be any shock wave crossing that matter, the matter would have remained cold. We wouldn't have any possibility to detect it. We detect matter when matter emits radiation. Whatever radiation is. Well, now we are in the gravitational wave era, so we can detect also mass which doesn't emit electromagnetic radiation, just gravitational radiation. Well, in that case, in any case, it's kind of radiation. And that's a different story. But in general, if we stay in the electromagnetic domain, if you want to see the presence, if you want to detect matter, you have to wait. You have to find a way to detect possible radiation emitted by matter. Shock waves are really effective in this because they heat matter up, and so then you can detect it. Very beautiful. So we will make we will consider two different cases. In the case in which relativity can be neglected, so the velocities, energies at play are non-relativistic. In that case, this is physics that have been discovered and described in, I would say, kind of 150 years ago, more or less, in the second half of the 19th century. That's why, so the conditions, the mathematical conditions that describe the shock that we will see today are so-called jump condition. Why jump? Because the discontinuity in these macroscopic variables that I was telling you, the discontinuity, if you plot a discontinuous function, it looks like a jump, just like that. Jump condition, because these are the conditions that have to be fulfilled across the jump, so across the shock. And they also, so they have a name. They were named after two scientists, Rankine. I always get confused. Rankine was a Scottish physicist, and Hugoniot was French. So for those who are interested in just finding names, Rankine and Hugoniot. And we will see there is a solution, which is very interesting in the case of a sudden release of a huge amount of energy. So a strong shock within a point in a fluid, a homogeneous fluid, there is a solution, an hydrodynamic solution, which is called self-similar solution. We will see why. And again, the solution bears the name of two scientists who independently found it. Zadov from the Soviet Union, for the former Soviet Union, and Taylor, a British physicist. These are of the Cold War time. Cold War time, in the sense that it's not by chance that nuclear explosions just fostered this kind of research. So independently, these two scientists found the solution which described, for example, the explosion of a nuclear explosion. So we will see that. There's also a relativistic analog. So while the non-relativistic shocks is something which is not only can it be found in astrophysics, but also, as I said, on what happens whenever you have something which moves in the air at a speed, at a higher speed than the speed of sound. And we know a lot of examples. Also planes, airplanes. You know very well. So in that case, you have the development of shocks, and can be used. The physics that we'll see today can be used there. In the case of relativistic shocks, well, if you are thinking of objects, macroscopic objects, there's no way we can accelerate macroscopic objects in the lab to relativistic velocities. You need to look at outside in the universe. As I was saying, gamma ray bursts are a fair example of this. So in order to describe, you have the completely analog conditions. So in the relativistic case, the Champ conditions, so conditions that make sure that energy, momentum, and the case number of particles is conserved, not mass, in case of relativity. They are also called Taub conditions, after the name of the American scientist who in the last century just found. So this is very recent physics. You see, it's 70, 60, 70, or 50, between 50 and 70 years old physics. This is very recent. And again, the analog for the subsimilar solution is called Blanford-McKee. And these are, again, science. This paper just is even younger than myself. The Blanford-McKee solution is younger than myself. So since I'm very young, of course, as everyone knows, so this means that this is really recent physics. So let's review very few examples, because these are so beautiful pictures that they're really worth a look. So this is a planetary nebula. So it's a star which is just during its long death. Okay, it's not gonna die as a supernova explosion because the mass is not large enough, but still as the kind of death that the sun, our sun, will go through. So just the outer layers just are expanding under the influence of this wind. So in this case, all this material which is expanding, it nevertheless develops a shock. And so this is the result of the shock. So again, matter get heated up, and so it emits radiation. Radiation, for example, because some energetic levels get excited, so you have lines, and so that's also the reason for the colors that you see. Oh, this is an example instead of a supernova. This is an historic supernova, you know. This is the very famous, Tycho Brahe, the kind of master of Kepler. He was lucky enough that Kepler was lucky enough that in his lifetime he observed 2 galactic supernovae. And in particular, the first one, which is also observed by Tycho, in fact, it is called after him, in 1572. This was a supernova. You see, this is a movie. You see here the year of the picture. This is a composite image. You see X-rays and also optical. If you pay attention, it goes from 2000 up to 2015. You see, you can clearly appreciate the expansion. So you can measure the velocity and compare with the velocity that you measure from the Doppler effect, from the absorption line that you measure. So you measure the velocity, you know very well the velocity, and you will see what kind of information can be inferred. But essentially, what's going on here from the point of view of the shocks? Well, matter is expanding at a speed which is orders of magnitude faster than the speed of sound. So there's the shock which gets developed, and as we will see, the physics, beautiful physics, the result of the shock is that the matter which is expanding is also shocked. There are a couple of shocks which develop, one into the interstellar medium, and the other one, which is called reverse shock, which crosses backward the ejector, the matter which has been ejected. But when a shock crosses matter, we will see that it turns kinetic energy into thermal energy. So the result is that the matter that has been shocked is heated up incredibly. But you know that when you have matter which is heated up, it emits radiation. For example, it gets ionized. So you have a lot of electrons and ions. So for example, Bremsstrahlung, if the density is temperature high, density, the ion density high, so Bremsstrahlung surely is at play. Not only that, but also you have some energetic levels that then can be excited, so you also have some lines. So that's why you see this. And you see all those kind of filaments that are expanding, because matter has been heated up by the shock. The shock wave is responsible for this emission, is essentially responsible because it's what turned kinetic energy into thermal energy. Beautiful. So let's go to study in detail what happens. In particular, let's consider the one-dimensional case of a shock. First thing to note is that we conveniently assume a steady situation. So a fluid which is in a steady state. So it means that there is no explicit dependence on time. So that all the partial derivatives with respect to times are just zero. First thing to. And then we assume, as I said, typically these explosions are just, they just originate from a point source. But then let's consider you are far enough so that you can assume, as I said, a one-dimensional case, so just a plane. So you have a planar wave expanding within the medium. So we consider two reference frames. That's very important to keep in mind. The one I showed here in this figure on the left is the lap frame, in which you see this line, this thick vertical line, is the shock. The shock is propagating rightward, from left to right. And SW, sorry, is the velocity of the shock wave. SW stands for shock wave. Here that I use two different colors to distinguish between what is the post-shocked fluid and the unperturbed fluid. Well, if the shock is moving from left to right, you immediately see, and the shock is here, you immediately see that the blue fluid is the fluid that is still unaware that a shock is about to come. So I used a cold color to mean unperturbed. Or another way to call it is upstream fluid, because if you think that this is a stream, this is upstream, and this is downstream. So I will be referring to the unperturbed fluid as the upstream fluid, and to the post-shocked fluid as the downstream fluid, okay? So clearly in the lap frame, the upstream fluid is not moving. We start from a very simple situation. Prior to the shock, the fluid is in equilibrium, doesn't move, the quietest situation you can think of, okay? So it's cold and it's not moving. Cold, what does cold mean? Well, it practically means the velocity, the thermal velocity of molecules, so connected with temperature of the fluid, is negligible with respect to the velocity of the shock. That means cold. So here I wanted to point out that contrary to what we usually assumed, we use the prime quantities for from the moving frame, and here I use the opposite situation because I will be carrying out all the calculation in the shock frame. So let me use, I just wanted to point out, but here the figure should be quite telling. The prime quantities, they refer to the shock frame, okay? So U1 prime, I call 1 the upstream fluid, so the unperturbed fluid. So everything which is 1 as a subscript means refer to this fluid here. Everything with 2 as a subscript means downstream fluid or post-shocked fluid, okay? So U1 prime is 0 because the fluid is not moving. The upstream fluid is not moving in the lap frame. in the lock frame. While as the result of the passage of the shocked fluid will be moving as a result. This is one of the consequences of the shocks. We don't know yet what it is, but we call it U prime, U2 prime. So the velocity of the fluid right behind the shock. Okay, here. And as we will see, the choice for the colors is not by chance, it's not accidental, because we will see that the result of the shock is also to heat up the fluid. So just, that's the reason why I used red, a hotter color. Now, it's much more convenient, calculations are much easier if you carry them out in the shock frame. So what is the shock frame? Well, it's a reference frame which is moving together with the shock. So by definition, in this reference frame, the shock doesn't move. So for example, so it has if we call X the only direction, which is the direction along which we have the motion, let's call X 0 the position of the shock in the shock frame. So the shock is there and doesn't move. But just relative motions, automatically, you immediately see that given that we are moving from one inertial reference frame to the other inertial reference frame, it means that in the shock frame, the velocity of the fluid now, of the upstream fluid, should be 0 minus USW. Here, given that the motion is all from right to left, instead of having to deal with all minus signs, we just call the positive direction. The convention is that the positive direction is from the opposite as here. So from right to left, okay? So U1 should be in principle 0 minus USW. Let's call just change sign, so just USW, okay? So the velocity of the shock. And if you think for a moment, if the shock is moving with respect to the upstream fluid with that velocity, USW, well, it means that if you are riding on the shock, you see the upstream fluid coming to you with the same velocity as in magnitude, of course. Easy, pretty easy. And as a consequence, in this reference frame, the velocity of the flow of the post-shock fluid will be, well, it's velocity here, U2 prime minus the velocity of the shock. But again, we use the opposite convention. So instead of U2 prime minus USW is USW minus U2 prime. We don't know U2 prime. That's part of the tasks that we set to ourselves. We want to calculate among the different quantities also U2, and also as a consequence U2 prime. We don't know. We don't know the velocity. We don't know. We assume we know all the conditions. We know U1. We assume we know the pressure of the amplitude fluid, the density of the amplitude fluid, temperature. What we want to know is all the dynamic variables, so the velocity of the fluid, and the thermodynamic variables describing the status of the flow of the shocked fluid. So what is ρ2? What is P2? What is T2? What is the temperature? What is the density? What's the pressure of the shocked fluid? That's the goal. So our goal is to find the variables, the thermodynamic variables that describe the status of the shocked fluid, okay? That's the goal. How can you do that? Well, just apply the equation laws that we've seen in, last time. And that's exactly what I did here in this system of equations. You should recognize immediately. These are mass continuity, so the continuity equation about mass, so mass conservation, linear momentum conservation. Here you have no forces, nothing, so momentum is conserved. There is no F, you remember? Here there's no F. And the third one is conservation of energy. You remember? Here you have this term here, and here you have the enthalpy instead of internal energy here, all defined per unit mass. But you see, this is general. Now let's focus on this specific case. Here, for the assumption that we made, the dependence of these quantities on space, they just depend on just one single coordinate, which is x, because we assume a planar configuration. So there is no y and z dependence. So this is a 1D problem. So first of all, as I said, we are in a steady situation. So all the partial time derivatives just cancel out. Just so. First of all. Second, let's figure out, well, the way, so let's, for example, consider the first one, divergence of this guy 0. Well, to think of what is this condition, let's think of the corresponding integral. This is the differential, this is the integral. So again, I'm exploiting Gauss-Green theorem. So the integral over a given volume, over a closed volume, of the divergence of a generic vector field f, I mean a generic vector field. Well, for the Gauss-Green theorem, this is also a surface integral of the flux of the same vector field integrated across the surface which defines the boundaries of the region of volume V. So we conveniently choose a volume which you see is a very thin volume parallel to the shock. How thin? Well, thin enough to include the shock, of course. But the shock, we neglect the width of the shock. So it means that this guy here can be arbitrary, provided that it is larger than the mean free path, of course, arbitrarily small. So let's assume that A is the surface of this part here, which is also here. So we call capital A the surface. But you see that we consider a vector field which is completely along X. This is a 1D problem. So being completely along X, it means that when you calculate, you see the flux across the surface of this element, it means that you can neglect the lateral contribution here because you can choose the width as small as you want. So the only contribution to the flux will be across the surface here and the surface here. But if the flux, if the generic vector field that you consider, F, is something with, for example, like this arrow here, it means that on this surface here will be positive, on this surface here will be negative, because here it's coming out and here it's coming in. And given that the two surfaces, A here and A here are equal, so if I call F2 the value I have here of the field and F1 the value I have here in region 1, it means that the two contribution is, this is positive, this is negative, so F1A minus F1A. And this is the flux. But this has to be 0. So we immediately see that it means that the vector field has to be the same, has to have the same value on both sides. So divergence in the 1D key, divergence of a field has to be 0. It means that in a 1D case, it means that essentially the same vector field has to be the same value on both sides of the shock. Easy. So if you understood that, then it's a matter of applying this guy to the three equations that we have in the system. So let's see what happens. Let's see each one at a time. So let's focus on the first one. Here you have the divergence of rho v, so the mass flux. So it means that the mass flux has to have the same value on both sides. We are in the shock frame, I remind you. So given that I call U1 the velocity of the shock, of the velocity of the fluid in region 1, and U2, it means that rho 1, U1, so is rho v here, has to be equal to the rho 2, U2 here. Just like that. Very easy. Let's see the second case. Well, again, we have only to consider the only interesting direction, which is the x direction. So here Vx or U1 or U2, depending on which side you consider. So this guy is just ρ1 U1 squared plus what? Well, this is the x, so P1, because you are in the region 1. And if you think this is the linear momentum flux, this is how much linear momentum is crossing a given per unit area in region 1. And if you think this second equation is nothing but conservation of linear momentum, you have an amount of linear momentum crossing the shock from region 1 per unit area, per unit time, and this linear momentum is parallel to the direction of motion, okay? And linear momentum you cannot either create or destroy. So the same amount of linear momentum per unit area, per unit time has to come out in the downstream fluid region. So the analog ρ2 U2 squared plus P2. And this ensures conservation of linear momentum. You have as much linear momentum coming in, crossing the shock from region 1. That's the same amount of linear momentum that has to show up in region 2. Shock cannot either create or destroy linear momentum. And finally, energy. You see, the flux is this guy here, which just appears to be a little more complicated, but it's not. You see, I should put ρ1 U1 open bracket, but you see, ρ1 U1 is already equal to ρ2 U2. So I can, the term ρv, I can just neglect it because the two are equal. I know it from conservation of mass. So I can just equate the two, what lies within brackets. So let's have a look. 1/2 v squared. So if you're here, 1/2 u squared. And then you have enthalpy. So I call W1 the enthalpy of the fluid in region 1. And here, plus phi, we are neglecting any possible conservative field. If you think, well, if I'm thinking, for example, of a shock wave propagating in the air, well, the air is subjected, of course, to the action of the gravitational force. Yeah, but in this case, if you consider a shock which is horizontal, that's completely negligible. The shock, the potential, or in any case, the change in the potential, the gravitational potential, have a negligible effect. So you can just consider the same value from both sides, so you can just remove it straight away. So you see, you have a system of three unknowns. Let's focus which are the unknown variables. We assume we know everything in which describe the status of the fluid, of the upstream fluid. So everything which one is known. We want to find the value of the post-shock fluid as a function of the conditions of the unperturbed fluid. So surely one of the unknown is the velocity of the shock, the velocity of the downstream fluid, U2. U2 is one of the unknown, as well as ρ2. We don't know the density of the shock fluid, as well as the pressure. We don't know the pressure. So we already have three. And then what do we have? Well, the enthalpy is pressure over density. We already accounted for them. But also internal energy. That appears to be a fourth unknown. No, it is not, because if we exploit the equation of state, you can think of the internal energy as a function of pressure and density of the gas. So it means that once you know pressure, density, and temperature, you know everything. Okay, so in particular, you will see in a moment why this guy. So the idea, and these equations, this system is called jump conditions. Or jump condition is a little bit more general. If you want to mean these very conditions, so in this case of non-relativistic shock, these are also known as Rankine-Hugoniot conditions. Beautiful. So this is the system you have to solve. As I was saying, what about internal energy? Well, we are talking about an ideal fluid. So you know very well the internal energy of an ideal fluid, you can think of something like CV, where CV is the molar specific heat at constant volume. Okay, so internal energy of an ideal gas, CV times T for 1 mole. But if you remember, in our study here from the previous class, we defined all these thermodynamic quantities: internal energy, enthalpy, entropy per unit mass. So if CVT is the internal energy of 1 mole, you have to divide by the mass of a mole to have epsilon, okay? And how can I express the mass of a mole? Well, just take the mass of an individual particle times the number of particles that you have in a mole. But this is the Avogadro's number. But you can express the Avogadro's number as R over K, where R is the universal constant of gases and K is the Boltzmann constant. So you can look at this formula here as CV times T as the internal energy of 1 mole over M times Avogadro's number. And here I wrote the Avogadro's number as R over K, just like that. If it is not clear, please ask. So you can now divide well, again, this is just I used here I use Meyer's relation. So instead, R can be also expressed as the molar specific heat at constant pressure, Cp minus Cv. And here it's just exploited just the equation of state of ideal gas. So kT over the singular mass is just pressure over density, again from equation of state. So you see, in the end, I was right when I told you that indeed you can consider the internal energy by exploiting the equation of state as a function of pressure and density. So that's why it's not essentially a fourth unknown variable. Once you know pressure and density, you already know internal energy. And it's convenient if you divide both numerator and denominator by CV. You know very well Cp over Cv is just gamma, the adiabatic index. And so this is a general expression for the internal energy of a fluid, of an ideal fluid, as a function of pressure, density, and adiabatic index. Gamma now is the adiabatic index, not the generic index, okay? And what we have in the third equation of Rankine-Hugoniot, if you remember, is enthalpy. So it's also convenient to find enthalpy. By definition, enthalpy is an internal energy plus. So 1 over gamma minus 1 plus 1, just for kids, is gamma over gamma minus 1. So enthalpy is just gamma over gamma minus 1, P over rho, just like that. But if you remember, from where the very first thing we saw this morning, the sound waves, the speed of sound is just square root of this guy here. You see, here you have gamma P over rho. This guy here is the speed of sound square. So it means that, and I called it CS. So this guy here is nothing but CS squared over gamma minus 1. Very convenient. Why? For the reasons that you will see in a moment. Let's define a new quantity, very handy, which is a so-called Mach number after the Austrian physicist Ernst Mach, who inspired so much Albert Einstein in formulating the special relativity, the relativity theory. And here the Mach number is a way of expressing velocities in units of speed of sound and corresponding speed of sound, which means that given that the speed of sound depends on pressure and density, and depending on whether you consider the upstream or downstream fluid, pressure and densities will change, so will the speed of sound. So the speed of sound has two different values with respect in the upstream and downstream fluid. So it means that when you want to express the velocity of the fluid, ui, where I can be 1 or 2, over the corresponding speed of sound, CSI, because that also depends on which side of the shocks you consider. So we call MI. M1, so will be capital M1 will be the Mach number, which describes the velocity of the upstream fluid in units of speed of sound in that region of the as well as M2 will be the speed of the velocity of the downstream fluid, again in units of the speed of sound in that region. That's very convenient, because if you think immediately, depending on whether M is larger, is higher, or lower than 1, you are dealing with a supersonic motion or a subsonic motion. So that's very convenient. Also very convenient because that's what you end up with. Here, this is the solution of the Rankine-Hugoniot. I strongly invite you to check it out. Make sure that once you define enthalpy like this, once you define M1 and M2, the two Mach numbers, so in particular, M1 is assumed to be known because it's a function of known quantities. So everything with 1 is assumed to be known. And if you think M1 is the velocity of the fluid, of the upper tube fluid in the shock frame, it is also, as a matter of fact, the velocity of the shock in the lap frame. So M1 is telling you the velocity of the shock in the lap frame. So M1 much larger than 1, it means that you are dealing with a very strong shock, a shock whose speed is very, very supersonic, okay, for example. So if you solve the system, you will find, you see, here I put the solution as a function of the corresponding downstream quantity as a function of the corresponding upstream. So the ratio of the corresponding quantities. So you see that the ratio of the two density scales in a reciprocal way with the velocities, and this is an immediate consequence of the continuity equation. And this is the solution. This is the solution for the pressure ratio as well as the temperatures. The temperatures, of course, is immediately derived from the equation of state. And here, aside, I also put M2, because M2 is, again, the velocity of the fluid, again, in the shock frame, as a function of the once quantity. First, here there are a few things to note. You see that you have the adiabatic index showing everywhere. So it means that you change the gas from monatomic to biatomic, for example, and here numbers changes a little bit, but change. So it depends also on the nature of the gas. Before going on with comments, I would like, as I said, I strongly advise you to check it out. Make sure you can prove the solution. I immediately tell you that's going to take quite some time. It's not straightforward. It took the very first, when I first did it, I had to battle away at some algebra. It takes a while, but it's really worth. So if you just have 10 minutes spare time, unless you have prodigious capabilities in just calculations, but I don't think you can make it. Just take your time. When you are bored, you don't know what to do, you're whatever, just you see, okay, now I'm going to prove the solutions of the Rankine-Hugoniot solution. It's very satisfying in the end when you get to the end. So now let's see, as a consequence, what happens. Well, here I can make a lot of comments, but it's more interesting to work out some comments in one special case, in the case of a strong shock. So this is the correct solution for any kinds of shocks. Okay, this is a comment I'm going to make later. Okay, let's focus on the strong shock case. Strong shock, it means that the shock is moving very, very fast. Very fast, it means that its Mach number, M1, is much larger than 1. So not only is the shock supersonic, but it's very, very supersonic. So if you take the other here, the most general solution, and you consider the limit of M1 very, very large, let's focus on, for example, on the first case. You see, it's like working the limit for M1 to infinity. Let's focus the first one. You see, you have M1 squared, both numerator and denominator. So it means that the ratio between densities, as well as the ratio between velocities, will not diverge, will tend to gamma plus 1 over gamma minus 1. And that's exactly what I wrote here. So it means that the density, even for a very strong shock, the ratio between the two densities is not arbitrarily large. It tends to a finite value. So for example, if you think of a monoatomic gas, this is 5/3, 5/3 plus 1, 8/3, 8/3 over 2/3 is 4. This ratio is 4. So it means that even in the case of a strong shock, the density in the downstream fluid doesn't increase arbitrarily. It's just 4 times more dense, not orders of magnitude, 4 times. Let's have a look at the pressure. You see, let's get back here. The pressure, well, here you have M1 squared. So it means that when M1 is very large, pressure P2 with respect to P1 can be instead arbitrarily, so correspondingly large. So in particular, the asymptotic behavior of the ratio P2, P1 is 2 gamma M1 squared. And in particular, so the ratio, unlike the ratio of densities, which doesn't change really, the ratio of pressure can be arbitrary, can be correspondingly large, completely different, you see. So even if the pressure in the upstream fluid is negligible, the pressure in the downstream fluid can be very large. And in particular, instead of the ratio, let's work out the absolute value of P2. You see, so P2 here, it is this guy here times P1. But P1, if you remember, is the it can be expressed as this guy here, in the sense that if you express M1 on one side is the velocity of the fluid, so U1 over the speed of sound. The speed of sound is P over rho. So P1, you have P1 rho 1. So P1 just cancel out. You are left with rho 1. And you see here, just forget about the numerical coefficient 2 over gamma plus 1. Let's focus on the physical quantities. You have P2 equals rho 1 U1 squared. Now, if those of you who remember when during the first the basic physics course, when I mentioned the so-called Ram pressure, so the pressure that an object which is moving within a fluid at a supersonic speed, the pressure that is developed the pressure felt by the object, that's exactly this guy. You see, the density of the fluid times the velocity squared. So the relative velocity between the object and the fluid. That now you see exactly the exact solution. Beautiful. That's exactly the ground pressure. And let's have a look at the ratio between temperatures. You see, T1 over T2 scales again have, apart from the numerical coefficient, has the same scalings as pressure. So M1 squared. So in particular, here, I just wrote the thermal energy corresponding, K2T, KT2, which is, apart from the numerical coefficient, is M1 MU1 squared. So you see, the temperature scales as the velocity squared. So scales correspondingly with the pressure. Now you see this the various of information that I told you. So look, when the object from the outer space, they get really, really hot. Why? Because they are moving within the air at a supersonic speed. So they develop a shock. There is a shock. The air close to the object is shocked. So the temperature of the air is really, really high. See?
Scusi,
Yes. Yes.
potrebbe ripetere dall'inizio della definizione di T2 fratto T1 il commento che stava facendo, perché saltava molto l'audio e io almeno non sono riuscita a capire praticamente nulla. Ora è tornato, va benissimo l'audio, quindi...
Allora questo conferma la mia ipotesi che non dipende dalla rete di casa mia, perché adesso sono qua.
Già.
Io credo che, io farò notare, ma non avete avuto altri problemi con altri docenti?
No.
Allora, il mio computer, allora non so più cosa succede. Perché allora non... Ok, grazie per avermelo fatto notare. Okay, so getting back to so please also let me know if you experience further problems. So the ratio between temperatures, you see, scales as M1 squared. So has the same scaling as the ratio between pressures. So it means that, again, if I express the absolute temperature instead of the ratio of temperatures, but the absolute temperature of the downstream fluid T2 as a KT, so as an energy, you see that it's like the kinetic energy of the individual molecule with the velocity is the shock velocity, the velocity of the shock in the lap frame, of course, with respect to the unshocked fluid. So it means that the fluid, the shocked fluid, is essentially has a very large pressure and it's very hot. And if you remember, when I was commenting also in your undergraduate course, if you think, for example, let's think of a meteorite which is entering the atmosphere, of a space shuttle. Whatever comes from outer space enters the Earth and so has a supersonic speed. There is a shock which develops in the air close to the object. So the air there, not only does it experience a strong pressure, which is the ramp pressure, but the temperature of the air is very high. And when people say, oh, things which cross the atmosphere get really hot because of the friction of air, that's a big mistake. There's nothing to do with friction. It's not friction which heats up. You see, here we have no friction whatsoever. We are considering an ideal fluid. There is no friction at all. And still, the air or the fluid gets really hot. There's nothing to do with friction. Of course, if the fluid is also viscous, of course, friction will add up, will sum up to this effect. But the main explanation for this object getting really hot is not friction of air. That's a mistake that sometimes people just hear. There's nothing to do with friction. That's the reason. So And that's unfortunately the reason. Probably you are too young, but in 2003 there was a disaster, space shuttle Columbia, which just was damaged. Elements, tiles, which were part of the heat shield, which shielded the spacecraft from tremendous heat that gets developed because of this. So one of the tiles was damaged, and then just it got temperature, got too high, and then it exploded. That's the heat. That's where it comes from. That's why temperature of the air gets really high, because you have a shock, a strong shock which develops. So the air, the temperature of the downstream of the post-shock fluid gets really high, you see. And what about the velocity of the post-shock fluid? Well, this is a piece of information which we told you about M2. Okay, let's get him back. M2, you see here, this is the general formula. Even when you send M1 to infinity, the limiting is gamma minus 1 over 2 gamma, which is this guy here. So the post-shock fluid is not moving arbitrarily fast. Even in the case of strong shock, the post-shock fluid will be moving with respect to the shock, not so fast, regardless of the velocity of the fluid upstream. So how can we summarize this picture? So even in the case of strong shock, you see, if you imagine, you see the shock, you see what happens here in the shock frame. You can imagine that you have the fluid just moving towards the shock at arbitrarily large, depending on M1. So can be moving very, very fast here. But what happens across the shock? That the velocity of the fluid here is not excessively large, because most of the bulk kinetic energy of the fluid that you have here turns into heat. So you have a lot of dissipation of kinetic energy into, I would say, random kinetic energy. Because if you think of the meaning, of the microscopic meaning of heat, it means that the kinetic energy of the individual molecules is high. So here you have a lot of kinetic energy with associated with velocity which are almost parallel. All the molecules in the upstream fluid are moving almost parallel. So that's what we call bulk kinetic energy, because they are moving just as a macroscopic object, which if you think in thermodynamic terms, it means something which can be used to make work. But when you turn this bulk kinetic energy into thermal energy, so thermal energy is still the molecules, the individual molecules have more or less the same velocity, so the same kinetic energy. But the big difference is that now here the direction is random. You have no bulk motion. Now you have thermal energy. So it means the thermal energy, you have the molecules have no bulk motions. They move in everywhere. So that's thermal energy, that's internal energy. But you know very well that you cannot use thermal energy to make work with no other result, of course. So you see how thermodynamic principles, laws are crucial in describing this. So again, in the case, so the dependence on the adiabatic index, for example, you can consider a monatomic gas. It means that the ratio between densities. So you don't have, even in the case of strong shock, you don't have a dramatic increase in density. Depends on a factor of a few, depending on the kind of gas. The velocity is downstream is not necessarily too high. And you see that this ratio is below 1. So it means that the velocity of the post-shock fluid is subsonic, is not supersonic. Even in the case of a strong shock, beautiful. What instead increases the mass dramatically for a strong shock is pressure and temperature of the post-shock fluid. Beautiful. And again, yes, here this is just so the shock indeed turns kinetic energy into thermal energy. So if you imagine, you can see the individual molecules moving from here upstream to downstream. So what changes is, as a matter of fact, is not the individual kinetic energy, the average individual kinetic energy of the molecules. More or less is the same. Is the when you're here, they are almost parallel. They move together as a kind of, not exactly, but kind of a single object. There's a bulky kinetic energy. But when they're here, every molecule just goes its way. So it's thermal energy because it's kinetic energy of individual molecules, but there is no common direction of motion. But from a thermodynamic description, that makes a big difference. That makes a big difference because you are turning work, kinetic energy, into heat, into internal energy. And if you think of the consequences, that's the consequences I wrote here. First of all, look, you cannot have a subsonic shock. If you work out, look, M1 cannot be lower than 1. So the upstream fluid, and 1 is the velocity of the upstream fluid with respect to the shock, but it is also the velocity of the shock in the lab frame. So this guy means that the shock, if you want to have a shock wave, necessarily the shock has to be supersonic. It's not possible to speak of a shock wave which is moving slower than the speed of sound. There's no way it's slower than the sound. It's not possible. If you want to develop a shock, the shock has to move, the motion has to be supersonic. Otherwise, you do not end up with a shock. And why this? Because you see, if M1 is lower than 1, look, this ratio here is the ratio between the two velocities of the shock. If M1 is below 1, it's something for kids. I already tell you, because gamma is larger than 1. So if you take this guy and set below 1, lower than 1, you immediately see that you have a consequence that U2 is greater than 1. But this is not possible. Why? Well, if U2 is minus 1, the other consequence is also that T2 is lower than T1. So if should this be the case, if M1 lower than 1 were possible, the immediate consequence for the solution would be that here the fluid is moving slowly and here the fluid is moving fast. So you have increased the bulk kinetic energy of the fluid. Who pays the bill? The thermal energy, because here you have hot fluid, T1, and here you have cold fluid. So from an energy budget point of view, it means that here you have slow and hot, here fast and cold. So you turn thermal energy into bulk kinetic energy with no other result. This violates the second law of thermodynamics. Beautiful. So you see the beauty of all this argument. You cannot violate the second law of thermodynamics. And because of that, the implication of this is that the shock has to be supersonic. There's no other way. Otherwise, it's not a shock. Beautiful. And now, if you think of the kind of transformation that happens across the shock, you turn bulk kinetic energy into thermal energy. But this is an irreversible transformation. You cannot go the other way. You cannot go backward with no other change. So it means that you've gone through an irreversible transformation right across the shock. But that means that entropy cannot be conserved. And indeed, the second implication is, the first one is that M1 has to be greater than 1 if you don't want to violate the second law of thermodynamics. The second implication is that the entropy in the downstream fluid has to be higher than the entropy per unit mass in the upstream fluid. because you went just across the shock. You went through an irreversible transformation. Second law of thermodynamics. You see, now you see why the second law of thermodynamics is so beautiful. It has so many implications, even in the fluid dynamics, you see. So now, if you remember the very last thing I told you when I was mentioning last time the equivalence between conservation of energy and conservation of entropy when we consider reversible transformation, you see that here when we wrote down the Rankine-Hugoniot conditions, in particular the third one, which is about the conservation of energy, should we have used the conservation of entropy, we would have made a mistake. Because in this case, across the shock, energy is conserved, entropy is not. So the two cannot be used in one as an equivalent of the other. Across the shock, because crossing the shock, the fluid undergoes an irreversible transformation. So entropy is not conserved. And the beauty, you see, that the beauty is that if you imagine you follow the value of the specific entropy across here, downstream, upstream, and then downstream, is always conserved then entropy under our assumption of an ideal fluid, in which we neglect viscosity, we neglect heat conduction, and radiative losses. But there's one point in which entropy undergoes a discontinuity, which is across the shock. So across the shock, which is exactly what we've been caring of today, is that entropy is not conserved. So energy conservation is satisfied, entropy is not. But then here, so the entropy is just, if you could plot the entropy function, this is just a step. This is like this, and then it has a jump upward because entropy increases, and then it's constant. This shock is also called adiabatic shock. Why? Because we neglect radiative losses. We assume that the gas is not capable of dissipating energy through the exchange of heat with its environment. Again, for the very same reason I already mentioned before. For some reason, maybe you might think of maybe there is some, in principle, could emit Bremsstrahlung. But if the optical depth is too large, well, the heat, the radiation is not capable of effectively carrying energy away. So that's why it's adiabatic. It's not effective. The radiation losses are not really changing the content of energy. So this is why this is referred to as adiabatic shock, because here you are neglecting the loss of energy due to radiation for many possible reasons. And the final comment is that indeed we proved a very beautiful piece of physics. We are dealing with ideal fluids. So if you think it's difficult to dissipate kinetic energy with you have ideal fluid, you have no viscosity. You just dissipate energy when you want to heat up your hands because you're exploiting viscosity, friction. This is friction of your hands. It's difficult to dissipate kinetic energy when you have no friction at all. When you have no radiation losses, no friction, that's the way ideal fluid can do that, through shocks, you see? Shocks indeed have dissipated kinetic energy and turned it into heat. The gas has been heated up, so you increase the internal energy through an irreversible process. You cannot go the other way because you went through an irreversible process. Very beautiful. I stop here. Tomorrow we will see a beautiful example of this physics applied to atomic bombs. And then no, not tomorrow, sorry, next on Wednesday. Okay. Any questions?